right, looking good. So, we'll hang out for just a minute or two, make sure everyone finds a Zoom link today. How's everyone doing? Good to see you, Arthur. Hey, Keely, always good to see you. Austin, Brandon, how's everyone doing? James, Eamon, Harvey, Roman. Hey, John, how you doing? Outer Banks, North Carolina, said Austin. Great. So we'll go ahead and get started. Yeah, I'm really excited. This is the book launch webinar series for the brand new book, the Mastering the PE Exam 100 Qualitative Practice Problems for the Electrical Power PE Exam. This thing is packed full of qualitative relationships. It's just about 270 pages. If you've worked through either of our other books, you know I'm extremely detail oriented. I mean, that's almost 300 pages for hundred problem solutions. Visual aids, circuit diagrams, formulas, all that great stuff. Really breaks down every problem. So, it doesn't matter where you get stuck or, which part of the subject you're trying to learn, that information is going to be provided there for you. Out of curiosity, who here is currently enrolled in our online class? Give me a one. Give me a one in the chat. Anyone currently enrolled in the online class? Wonderful. Lots of ones in the chat. Great. How about anyone not enrolled? Give me a two. Anyone studying for the PE exam that's not enrolled in our online class? Great, some twos as well. Glad you guys could enjoy us. If you are taking the PE exam this year, we did just start the winter 2025 live class semester. We'll be doing live classes twice a week from now until about April. So if you are taking the PE exam this year, it's a great time to jump in, get some hands-on learning with myself and the rest of the class. Great. So this is webinar 1 out of 4. I'm going to be doing these every Thursday for the next 4 weeks. If you registered for this one, that means that you already registered for the future ones as well, which saves you some time. But the upcoming dates, of course, today is January 9th. Next Thursday will be January 16th. The Thursday after that is January 23rd. And the last Thursday that we'll be doing this book launch webinar series is January 30th, 2025. They'll each run about an hour. I'll try to keep it right at that hour mark. And if you're on the East Coast like me, they all start at, noon, right? 12 o'clock p.m. So depending on your time zone, it might be a little different. So the book is live right now on Amazon. I currently have it set to it's the lowest price Amazon will let me sell it for. It's $20.50 if you're interested in buying an early copy. Easiest way to find it is just search my name on Amazon.com. Search Zach Stone, but include the PE at the end. It's the easiest way to pull my author profile. You'll see all of our books, not just this one. My plan is I'll probably keep it at this $20 price for the next few weeks while we do this seminar. I actually get $0 at that price. It's the lowest price Amazon will let me sell it. It's essentially at cost. And the reason is, really just trying to get this book in as many hands as possible up front. And, it's a early book launch party. It kind of gives an incentive to grab it early. But yeah, I receive exactly $0 at this price. So grab it while you can. If you are enrolled in the online class, I will be making the PDF available probably in the next month or two. We're still working out the bugs to that. But $20 price currently, if you have Amazon Prime, you get it shipped to your doorstep in 2 days. It's a great bargain. Minha said, yeah, the recordings. So these webinars, I'll be recording all of them. We're going to post them to our YouTube channel probably same day. So you'll be able to watch the recordings of each webinar. Each webinar is going to be different. I'm going to work different problems from the book. There's 100 problems in this book, and they're divvied up into sections that align with our class schedule. Starting with circuit analysis, then transformers, then motors, devices in power electronics, so on and so forth. Most practice exams will have all the answers and solutions all the way at the end. I really think the best way to work through this book, especially if you're in our online class, is to work in these problems as additional homework with each class. So, for example, next week we're doing circuit analysis on Tuesday and Wednesday. That'd be a great time to work through the 10 circuit analysis problems in the very beginning of the book. And immediately after just the circuit analysis problems are the circuit analysis solutions. And then same thing. Next week, after we cover rotating machines, the following week on Tuesday and Wednesday, that would be the best time to work the 10 rotating machine problems. And again, the solutions follow each subject, just so you're not digging at the back of the book each time. You can work it as a practice exam. Keep in mind there's 20 more problems than typical, right? 100 problems instead of 80, but it's totally up to you how you work it. Great. Daniel said my copy is being shipped this Saturday. Great. So the way we're going to do these webinars is For today, I pulled the first question from every subject. We'll see how many we can get through. Are we going to be able to get through all nine? Probably not, right? I'd be pretty impressed. But every Thursday, we're just going to pick up right where we left off. So we'll see how many we get done today. That'll give me a good idea too to plan for the future weeks. But the best part of these webinars, you get to ask questions. So I'm not going to try to rush. We're going to try to take our time, have a really good discussion. One of the fastest ways to learn anything new, not just the P exam, is really being able to engage in dialogue. So any questions that pop up, now would be the best time to ask them, and we can have those kind of sidebar discussions related to each problem. How's that sound? Let's see. Rana said, "What's the approximate frequency of qualitative questions on the PE exam? What's the current trend?" Great question. Has anyone here taken the PE exam recently? By show of hands in the chat. Anyone here taken it recently if you've already taken it before and you weren't successful? So quite a bit. How many, you saw quite a bit of qualitative practice problem or qualitative questions rather on the exam, didn't you? So Rana, there's no actual number. NCS doesn't publish that. But if you've been paying attention, Facebook, Reddit, LinkedIn, on our online community, powerpehelp.com, you'll notice that people are saying that the PE exam is becoming more and more and more qualitative. Yeah, I'm seeing a lot of you saying there's a lot of qualitative problems that you ran into. Um, so what does that mean? That means in order to pass the PE exam, you got to be less reliant on your calculator, less reliant on formulas. Now, the good news is a lot of these qualitative questions, I'm going to show you how you can solve them using formulas. Typically, I refer to these as quantitative questions in disguise as qualitative questions. A lot of these problems, we're looking at the formulas and we're seeing what happens if I change one variable. How does that affect the other variables in the formula? So a lot of these problems, kind of think of them as quantitative problems, quantitative being numbers, but without numbers, with just variables. So I've got all sorts of tricks to show you how to do that. Um, Not everything can be solved that way, but plenty of them can. Do some questions rely on career experience, industry experience? Sure. That doesn't mean you can't learn them, right? We cover quite a bit of qualitative aspects in our online class too. But yeah, this book is a fantastic resource. I mean, it took me a little over a year and a half. It almost took about 2 years to knock out, and really covered it all from A to Z. So it's a fantastic resource. You're really going to learn a ton. You're going to be able to apply it towards all sorts of different qualitative problems for the P exam. But yeah, but that's why this book is so important. It's really going to prepare you for the qualitative side of the P exam. Once you work through this book, you will never be intimidated by qualitative problems. You'll know exactly how to approach them, even if you don't have experience working with them. All right, sounds good. You guys ready to get started? Let's go ahead and try the first problem. All right, problem number one, circuit analysis. So I'm going to take my time. I'm going to read the question, read the answers. And as soon as you think you know the answer, give me an A, B, C, or D. Give it to me right in the chat. So number one says three identical complex single-phase loads are delta connected to make a complex three-phase load. Assuming balanced conditions, select the answer below that describes what would happen if the same load was Y connected instead. In other words, I've got three equal impedances, they're balanced. Those three impedances are currently connected in a triangle and a delta connection. If I take those same three impedances, if I unconnect them as a delta and then I reconnect them in a Y connection, what happens? So A, the load would draw the same amount of current. B, the load would draw 1.73 times more line current. C, the load would draw 1.73 times less line current. Or D, the load would draw three times less line current. Of course, everyone knows what 1.73 is, right? Especially in electrical engineering, that number comes up a lot. 1.73, that's just what? That's just the, yeah, square root of 3. All right, what do you think? A, B, C, or D? All right, seeing probably 50-50 split in the chat. I'm seeing mostly A's and D's. I see a couple of C's in there, but I'd say we're about 50-50 between A and D. So look, I added this diagram right before we started because I just wanted to really demonstrate what the problem is saying. So we've got three equal impedances, right? Three complex Z's. And currently those are delta connected. So I take these three equal impedances and I unconnect them from each other. And then when I reconnect them, I'm going to connect them instead in a Y configuration. When I do that, what are we assuming does not change, right? If this is a load connected to a power system, what are we assuming does not change? We know it's a three-phase load, right? It's either delta or Y. Delta Y connections, of course, three-phase connection. Yeah, the impedance does not change, but more importantly, the voltage. Great job, Charles and Michael. Yes, we're assuming that whatever voltage that this load is connected to, it's the same voltage, right? Problem didn't say, hey, we're connecting this to a different power supply or anything like that. So whether it's a 208 three-phase, 480, 4160, 13.8 kV, doesn't matter, right? We're assuming that that line voltage, the voltage from A to B, B to C, and C back to A, whether it's delta or Y, same line voltage, right? Same line voltage. All right, well, let's take a look at the answer. So those of you that said D, you are correct. The load is actually going to draw three times less line current if we change the configuration from delta to Y. How can that be? So first, I've got the exact solution from the book, but I'm just going to explain it to you and draw it out. It's easier, but you're also more than welcome to read along. First, the easiest way to understand it, let's look at the Y connection first. So here's our Y connection. Here's the equal impedances, right? We're interested in changes to this line current right here. So I got to come up with a formula or a relationship that solves for the line current of this three-phase Y connection. Here's our three-phase line voltage that we talked about. Whatever it was when it was delta connected, same thing. When I solve for line current using impedance, what formula do I use and what kind of circuit do I need to use, regardless of it, if it's delta or Y? Does anybody know in the chat? What formula and what circuit do I got to use? I'm going to use Ohm's law, right? V equals IZ in the general form. This time, of course, we're solving for the current. So I equals V over Z. And what kind of formula is Ohm's law? What kind of formula is this? Even if I want to use it for a three-phase system, it's what? Yeah, it's line to neutral. Great job, Mark. Or it's a single-phase formula. Yeah, you got it, Lewis. So if I want to use a single-phase formula or a line to neutral formula or a per-phase formula for a three-phase system, I got to model it how? I've got to model it using, you got it, Jason and Arthur. We got to model it using the single-phase equivalent circuit. So on the right, single-phase equivalent circuit of our three-phase Y connection. We're essentially modeling one phase of a balanced Y connection. What happens to the voltage? What's my voltage on my single phase equivalent circuit compared to my line voltage? What does this V phase equal compared to my line voltage over here? I'm going to take my line voltage and I'm going to do what to it? And you can assume we're just working with magnitudes right now. Yeah, divide by the square root of 3. This V phase, it's the phase voltage of our Y connection, which means it's really what? It's really the line to neutral voltage. We're looking at the voltage right here, plus V phase minus from the line connection to the neutral. All right, when I model a single phase equivalent circuit from a Y connection, do I have to change the load at all? So do I have to change anything to the impedance? No, no change. We get to, if you've been in class, you know, we get to take that at face value. Now, what's the neat thing about a single phase equivalent circuit? What's the whole point? And if you've been in class before, I like to call it, what's the magic? What's the magic of a single phase equivalent circuit? Yeah, Lewis and Jared and Jason. The magic right here is that the phase current, I phase, in the single phase equivalent circuit, it equals the line current of the system we modeled it after. That's the whole point of a single phase equivalent circuit. So using Ohm's law, look, here's Ohm's law for the line current drawn by this balanced Y-connected impedance. It's just I equals V over Z. I can say the phase current in my single phase equivalent circuit equals my phase voltage in my single phase equivalent circuit divided by the impedance in my single phase equivalent circuit. And of course, again, the phase current in our single phase equivalent circuit, here's the magic. It equals the line current of the system. Whole point of using a single phase equivalent circuit. So in Ohm's law, I'm just replacing I phase with I line. All right, we're going to compare this relationship, our Ohm's law for the line current drawn by the load when it's Y connected. We're going to repeat the same process, but with the load delta connected instead. Then we'll see what's different. We'll see if the Y connected load truly does draw 3 times less line current. You guys ready? Let's check it out. So here's our three-phase delta connection on the left. You'll notice I'm using the same exact variable Z for the impedance in each phase of our delta connection, just like I did in our Y connection up here. No change, just variable Z. Can anyone tell me why am I doing that? And I'm not specifying this is YZ and this is Y delta. Why am I using the same exact variable? What did the problem tell us? What was the whole premise of the problem? The problem says, hey, we've got 3 single phase balanced impedances. They're equal. We're going to delta connect them in a triangle. That's right here. And then we're going to delta connect them, or excuse me, we're going to Y connect them. That was the previous page. So they're what? Impedance stays the same, says Joey. Charlotte says equal impedances. Yes, we are not working with equivalent impedances. That's a different type of problem. This problem, we're using identical equal impedances. It's the same impedance. We're just breaking apart the delta connection and then reconnecting it as a Y connection. So that's why we have the same exact variable Z. That's going to let us relate the differences to the line current. All right. Unlike the Y connection, when I model a delta connection as a single phase equivalent circuit, what do I got to do to the impedance in each phase? If I want to use a single phase equivalent circuit to model a delta connection, do I get to take that impedance at face value and stick it in my single phase equivalent circuit? No, I got to divide it by 3. Great job, Jennifer, Lewis, Austin, Jared, and Mike. Very important. Big change right here. Now, a question. V phase. What is this equal to in relation to our system line voltage? Is it going to equal the system line voltage? Because, well, hey, I thought for delta connection, the line voltage equals the phase voltage. Is that true or is that a common trap? We still do what? Good job, Lewis. Careful, that's a trap. That's not the phase voltage of our delta connection. Look, I'm not looking at this voltage from here to here. I'm not looking at the delta phase voltage. This is not a delta connection on the right. This is now a single phase equivalent circuit. Look, if I was looking at this voltage, that would be my delta phase voltage or equal to the line voltage. But across that voltage measurement, I have Z. Across this voltage measurement, I've got Z over 3. This is still our line to neutral voltage. This is the line voltage divided by the square root of 3. This is not the phase voltage of our delta connection. This is the phase voltage of our single phase equivalent circuit. Phase voltage of the single phase equivalent circuit, it's always the line to neutral voltage. Always. All right, we're going to use Ohm's law again. We're going to solve for the phase current inside our single phase equivalent circuit. And since it's a single phase equivalent circuit, here's the magic. Our phase current is going to equal the line current of our system, this guy right here. And remember, we're trying to compare the two line currents to see what happens. So here's Ohm's law again. I equals V over Z. My current is my phase current of my single phase equivalent circuit. I'm going to replace it with my line current. I'm going to swap the variables because they're equal. That's the whole point of a single phase equivalent circuit. Next comes my voltage. My voltage V is still my line to neutral voltage. It's still the phase voltage, again, not of the delta. It's the phase voltage of the single phase equivalent circuit. So no change here compared to the previous formula when it was Y connected. What do we divide by now? What's the total impedance in the circuit? Is the total impedance in the circuit equal to just Z like it was before when the loads were Y connected? Is it equal to just this Z? What do we have to do to the impedance to model the single phase equivalent circuit when it was delta connected? We had to divide Z by 3. So here's the change. The only change in our Ohm's law formula compared to the previous page when they were Y connected is the 3 in the denominator of our impedance. That's it. So to make this easier to look at, instead of dividing a variable by a fraction, I can take this 3 and do what to it? I can just bring it all the way up to the top. I can bring it to the numerator right here. So that's all we did. Here's that same 3. All right, we're done. All we got to do is compare them. We came up with the Ohm's law formula to solve for the line current of that impedance, same impedance, never changing, if it's Y connected and if it's delta connected. Same impedance, right? So let's look at the difference. Here's the Y line current, what we did on the previous page. Remember, there's no 3 here, right? Line to neutral voltage or phase voltage of the single phase equivalent circuit divided by the impedance since it was Y connected. There's our line current. And here's the delta line current that we just solved for on this page. Here's this 3. So we can say one of two things. We can say that when that load is delta connected, it's going to draw 3 times more line current compared to if it's Y connected. Or we can restate that the way the problem said it. We can say when it's Y connected instead, that same identical impedance, no change to the impedance, it draws 3 times less line current compared to the delta connection. Does that make sense? And that's the answer. Notice so this is Ohm's law on both sides. The only difference is what? Is this 3. Everything else is the same. I've got the line current equals on both sides. Line to neutral voltage divided by the impedance. Line to neutral voltage divided by the impedance. The only difference is we multiply that whole ratio by 3 when it's delta connected. Or I can say I divide this whole thing by 3 when it's Y connected, meaning if I divide it by 3, the 3's go away. So final answer, when that impedance is Y connected instead of delta connected, it draws 3 times less line current. Interesting. All right, any questions on this one? I take a long time to explain it because I want to explain all the ins and the outs, and there's a lot of traps in here, a lot of nuances. Once you get the hang of it, this is a 2-second problem, I promise. Once you've drawn this out, work through the math, work through the numbers, it's quick. And you can even plug numbers in here if you wanted to prove it. Let's see. Min said, isn't the three-phase line voltage equal to phase voltage for a delta connection? Yeah, sure is. This voltage right here across this impedance, that's the delta phase voltage. And that equals the system line voltage. But that's only true for what? That's only true for delta connection. When we use the single phase equivalent circuit, we're always modeling the system using one phase of a balanced Y source connected to a Y load, which is why we have to divide the impedance over here by 3. If you're currently enrolled in class, we spend a good amount of time on this next week on circuit analysis. It's one of the most fundamental keys of using that single phase equivalent circuit. If you're not real comfortable with that, you won't be able to use that tool. Single phase equivalent circuit, wonderful tool. Wonderful tool. We got to know how to use it. Daniel asked, yeah, if you're enrolled in the unlimited package, Daniel, you'll have the whole PDF of this book once we're able to launch that within the course. Should be about a month and a half, month and a half. But yeah, you'll have access to it. Limited package or a monthly subscription. Any paid enrollment plans, you get access to all of the new content at no additional cost. Daniel said your explanation was perfect. I just have been out of school for almost 10 years, so I need more practice. Great. Yeah, Daniel, and this relationship bites just about everybody the first time around, especially because, hey, I thought anytime I see V phase, if it's delta, I thought that equals V line, right? Delta, V phase equals V line. That's only true when we're looking at the delta connection. Doesn't apply to single phase equivalent circuit. This problem bites everyone all the time for the first time. It's why it's problem number 1 in the book. All right. A lot of good questions. Let's just go ahead and we're going to move forward. We're going to try to cover some more ground. But remember, this recording will be up on YouTube, so you're more than welcome to rewatch it. More than welcome to ask more questions on the YouTube channel once it's posted. More than welcome to ask questions about this problem on our online community. Even if you're not a student, powerpehelp.com. It's the largest online community for help with the Power PE exam, absolutely free. Anyone can register. We make that available as a free resource for anyone. All right, problem number 2. This is like really problem, I think, 11 in the book. Transformers. Select the statement that accurately describes, here's a scary vocabulary word, describes hysteresis losses in transformers. A, power loss due to domains in the iron core reorientating themselves with the alternating magnetic field. B, power loss due to circulating currents in the iron core that dissipates that heat. C, power loss to current flowing through the transformer windings that dissipates as heat. Or D, power loss due to the current flowing through the rotor windings that dissipates as heat. Can we eliminate one obviously wrong answer at least? Seeing a lot of A's. Great. Anyone else? I'm seeing just about all A's. Good. I think I saw one B in there. Ooh, careful, Mark. Eliminate D, said Austin. Yeah, eliminate D. Multiple choice. If I make a guess, I've got 25% chance. I got a quarter chance of just blindly being correct. If I can eliminate at least one problem, my odds have now improved to 33.3% randomly guessing. Why can I eliminate D? Why is D the obviously wrong answer? Yeah, Michael said no rotors in a transformer. All right, so just about all you got this right. The answer is A. A lot of foreign, uncomfortable, intimidating sounding vocabulary words if we're not familiar. But if you're familiar with just even the basics of transformer losses, keywords like hysteresis, eddy losses, core losses, copper losses, heat losses, I square R losses, it's actually a pretty easy problem. So problem is A, power loss to domains in the iron core, reorientating themselves with the alternating magnetic field. What is a domain? And I've got an additional diagram here to talk about some of the other losses, but what's a domain? YouTube channel, yeah, just search electrical PE review. I'll pop right up. So here's the iron core of a transformer, right? If you've ever seen inside a transformer, it's really neat stuff. They're really thin. It's like almost a sheet of paper, thin piece of iron that's laminated. And they stack these sheets of iron to make a core that the windings then wrap around. Iron is a ferromagnetic material. It's like a conductor for flux. Instead of current, flux is flowing through the core. That's what allows the voltage to induce current into the other winding, even though they don't physically touch. So here's our iron core. Here's in the transformer equivalent circuit, that parallel branch, that's what we use to represent the core. Remember, the core is what the windings wrap around to make those transformer windings. So inside the core, we've got these little itty bitty things called domains. Sometimes they're referred to as dipoles, but proper term is domains. Think of a domain as you can't see it, right? We're on the like atomic level. Domains, it's the polar magnetic, trying to think of the best way. It's like you're looking at the atoms, right? You've got all these charged poles being north and south, right? Normally, I'm just going to draw one here, right? But there's so many. They're going to be randomly aligned when there's no power. When we apply power to that transformer, now there's flux in the core. Once a flux is flowing through the core, all of the domains want to do what? They want to go from randomly aligned, whether in this direction, this direction, this direction, this direction. They're going to all align in direction with the flux. So think of this as like a north and south pole. Think of like a bar magnet you played as a kid, but like on the atomic level, and there's thousands of them, millions of them. So when they go from randomly aligned, when there's no power, to turning the power on the transformer, applying a flux in the core, they're all gonna line up. It's like standing at attention. And when that happens, a lot of heat gets released as they change. Think of it almost like a friction heat. And that's exactly what hysteresis losses are. Let's see. Hysteresis losses occur due to the constant change in direction. Yes. And with AC power, the direction of this flux changes back and forth 60 times a second, right? For 60 hertz. If my AC power is a AC sinusoid, right? Here's 60 hertz, right? Or 1 over 60 hertz period. Every time the sine wave goes from positive to negative, the flux is changing direction, just like the voltage is changing direction, just like the current is changing direction. So every time the flux changes, because it's an AC signal, the domains are constantly swapping backwards, forwards, backwards, forwards. And that's the hysteresis losses. Make sense? Like most losses, it's released as heat. All right, other possible answer choices that were incorrect. Who can tell me what's an eddy loss? What was B? Eddy losses. You typically hear hysteresis and eddy losses used commonly. What's the eddy loss? Losses between laminations. Close. I don't necessarily think it's between. Little circulation, says Charles. Yeah. So eddy loss, that term comes from eddy currents, water currents in a river. It's exactly where that comes from. If I look at a river, a bed of this isn't an analogy. This is if we're looking at a real river, you get little pockets of kind of like circulating little currents on the edges of the riverbeds. So that circulating current, we use that same terminology applied to electrical current. So if we talk about those iron core sheets, here's just one sheet. Here's one individual sheet of iron. When we apply flux, when we induce voltage and current into the secondary winding, we're also inducing a little bit of current circulating in the iron sheets. Those are eddy currents, and the power losses due to the current circulating in the iron laminations is the eddy power losses. They also dissipate, like all power losses, as heat. All right, answer C. What's the copper I squared R losses? And why are we taking the time to go through each answer choice? This is just one problem, right? But really, this could have been 4 different problems. We could have asked about eddy losses, could have asked about copper losses, could have made a motor problem, asked about rotor losses, right? Anytime you answer a problem in the P exam, try to figure out why the incorrect answers are not the right answers. You'll get way more practice out of each problem. But it's kind of like we're turning one problem into 4. Daniel said, I appreciate your in-depth explanation of each answer. Great. Thank you. Yeah, it's more time consuming at first when you study, but you gain so much more ground this way. It's really the only way to learn. Let's see. Romello said I squared times RC represents the copper losses. Careful, not RC. This is the core loss resistance in the core. Here's our total winding resistance in our transformer circuit. As I2 over A, as this current flows through the total winding resistance, that's our copper I squared R losses. This resistor in the circuit right here represents what we think of when we think of transformers. When I think of a big winding on the primary, big winding on the secondary, this resistor, REQ, represents both the primary and secondary winding resistance, the winding of the actual copper conductors that the current flows on through that transformer. Why are these I squared? Why is it copper called copper losses? Well, that's the copper conductors wound into the transformer winding. Why is it called I squared R losses? Well, if I wanted to calculate the amount of power dissipated, I'm going to call it PEQ, or actually we'll call it PCU for P copper. How would I calculate the power dissipated in that resistor, which would give us the copper losses? It would give us the I squared R power losses. What formula do we use? We use the formula that's if I want to know power, real power P in watts from current and R resistance, the formula is I squared times R. That's the I squared R losses. In this case, the R is the total equivalent winding resistance. In this case, the I, we'll put a parentheses around it and then we'll square it. It's the I2 over A current, which is just the current on the secondary. A is just a transformer ratio. All right, last one. Rotor copper losses, not even shown, right? This is a transformer approximate circuit. We're not even talking about motors. I will point out though, look, the eddy and hysteresis losses, where do those occur? So hysteresis losses was the answer, right? But hysteresis and eddy losses, where in our transformer equivalent circuit does that occur? Yeah, in the core, said Taylor. RC in the core. This is usually they refer to this as PC for P core. You may have heard this as P no load or no load power losses. Same thing. They do not vary with the square of the current, unlike our copper losses. Yeah, your core power, it's the sum of your eddy and your hysteresis losses. All right. Any questions before we move forward? Careful, not X of M. Remember, um, really important, whether you're dealing with motors, transformers, transmission lines, when we say power losses. So in electrical engineering, we have up to 3 different types of units for power, right? We've got volt amps, if we're talking about apparent power, magnitude of complex power. We've got real power P in watts, and we've got Q for imaginary or reactive power and units of volt amps reactive. When we're talking about, anytime we hear the word power loss, which of these 3 types of power are we always talking about? Are we talking about just one? Or are we talking about 2 of them? Or could it be all 3? We're only talking about what? Only talking about real power P in the unit of watts. That's it. No power losses in the magnetizing reactance in the core. No power losses in the leakage flux or in the leakage reactance. That models the leakage flux. That little trick there will save you some points on the exam too. Arthur said, what would those reactance losses be called? There are no power losses. Reactive power travels back and forth from the power supply to the load, back and forth. It's just changing. Think of like a 2 water balloons. One's filled with water and they're just sitting there moving water back and forth. There's no actual water. Whereas think of your real power losses in watts. Think of it as like a slow pinhole leak, where your real power is lost. It's dissipated as heat. Here's my little fire sketch. It's dissipated as heat to the atmosphere. You'll lose it from the system. Yep, Taylor, you got it. Imaginary power. It's what in your inductors, that is what creates the magnetic field. And just like we talked about the flux on the previously, when we talked about it changing directions with AC power, your magnetic field around these inductors, we could show like a magnetic field around it. It grows during the peak, and then it shrinks to zero when the AC power or the AC voltage goes to zero. When the AC voltage then goes negative, it then grows again, but in the negative polarity. So it's constantly expanding that magnetic field around the inductor, going to zero, collapsing, and then expanding in the opposite direction, opposite polarity. But yeah, you got it. All right. Number three, what we got? Synchronous machines, one of my favorite subjects. I'll zoom all the way in so we can read it nice and clear. All right, what do we got? A, B, C, or D? This is a quick one. What information, but I'll get a lot of people with it. What information does the code letter on an induction motor's nameplate primarily represent? Is it A, the motor efficiency? Is it B, the locked rotor kVA per horsepower? Is it C, the torque for speed curve characteristics? Or is it D, the type of motor insulation? All information you can find on a motor nameplate. All right, I'm seeing B's, mostly B's. I see a couple of C's. I see one A. What do we got? I see a couple of D's. Code letter. Careful here. Code letter. Not to be confused with what letter? Not to be confused. So code letter is not the same thing as what other letter? Very commonly confused. Design. Good job, Lewis, Michael. Not design. I got a splinter on my finger today, unfortunately, when I was walking the dog. So if my handwriting is a little messy than normal, I chalk it up to that nasty splinter. I had to dig in my fingernail with tweezers this morning. Yeah, what's design letter? Design letter is what? NEMA. This is your NEMA design letter. What does the NEMA design letter tell us? Yeah, speed versus torque. Great job, Taylor. The different NEMA design letter tells us the difference between the speed versus torque characteristics. In other words, anytime you see this graph, and I think they've got this graph for a NEMA B in the reference handbook. You've got your locked rotor, pull up, breakdown. Again, not my best drawing, so catch me a break here. Here's our rotor speed. Here's our percent torque. Here's locked rotor at starting. Here's pull up. Here's breakdown. And right around here would be like rated speed, 100% rated torque. Different NEMA motors have different torque characteristics, meaning the torque of a motor, it's not linear. Oh, drop my pen. Hang on. The torque of a motor, we can say it's approximately linear in this region from breakdown to rated. Rated is where we want it to be. It's where it's designed to operate. Everything up in there, it's before then it's a roller coaster, right? Linear means straight line. So it's about a straight line between these 2 points, pretty close, but everything before that's a wild ride. So the different NEMA design letters, not code letters, tell us how that motor behaves, how much torque it outputs while it goes to rated speed. Different NEMA motors are used for different applications. Do I need a high starting torque, low starting torque, high efficiency, whatnot? All right, so the answer is B. The code letter, not to be confused with design letter, that's how we look up in the National Electrical Code, table 430.7b. That's how we look up the locked rotor information. So I pulled this right before we started. I use the NFPA link. If you don't use it, it's a great resource. I think it's like 14 bucks a month. You can access just about every code that's on the P exam except for the NESC, I believe. But anyways, here's the 2017 NEC because that's what they're testing on still, 2017. We go to 430.7. B is the locked rotor indicating, there it is, code letter. That code letter, you'll see it stamped on the nameplate. You'll just see a letter. Say we had the letter B stamped on it. It's not NEMA design B. It's code letter B. It's the letter that corresponds to this table, 430 7B, the locked rotor indicating code letter. And regardless what the voltage is of the motor, if it's a B code letter, I know at locked rotor conditions, aka when that motor is not energized and I push the button, the second it's energized, it's going to draw anywhere from 3.15. See if I can zoom in a little more. It's going to draw anywhere from 3.15 to 3.54 kVA per the horsepower rating of that motor. And then from there, we could convert it to amps if we wanted to estimate the range of locked rotor current. Does that make sense? Arthur, no word on when they're gonna start testing on the newer NECs. Hopefully not for a while, because I've got a lot of 2017 NEC content to I got to update. I think when that time comes, that'll probably be. I've been putting off making a code book. When they finally do update, that's when I'll probably publish a code book, though. Douglas, great question. What language would they use to indicate the NEMA design letter? Typically design. Design is typically the context, the keyword, or NEMA. Usually, if it's a good question, it'll say NEMA design B, NEMA design letter B, NEMA B, design letter B, all the same thing. But if you say code letter B, the second you see code, here's the way I think about it. When I struggled with this when I was working in design many years ago with motors, code letter tells me I'm referencing what? Tells me I'm referencing the National Electrical Code. That's what I remember. Taylor said, can this be used to dial in trip settings? Yeah, yeah. That's how the NEC instructs you to calculate the code letter, the locked rotor current. All right, 12:47. Let's see if we can squeeze in a few more here. Is this a good pace so far for everyone? All right, here we go. Number 4, making good time, devices and power electronics. In an AC system, the voltage and current are both purely sinusoidal with the same frequency. What is the frequency of the instantaneous power of the system? Is it A, the same frequency as the voltage and current? Is it B, twice the frequency of the voltage and current? Is it C, it varies depending on power factor? Or is the frequency 0? A, B, C, or D? What do we think? I'm seeing just about all B's. I see a couple A's. I'm seeing all B's. Great. Those of you that said B, why'd you say B? I was expecting to get more of you with this one. S equals VI. Great job, Austin. Yes. That's in the phasor domain, though. Phasors and RMS. When we're dealing with instantaneous, similar, we still take the product, right? But we're taking the product of those two periodic or instantaneous sine functions. But yeah, absolutely correct. All right. Yeah, the answer is B. Why is it that the instantaneous power is always going to be twice the frequency of the frequency of the voltage and current? We're assuming we've got like a balance system. We're assuming 60 hertz. We're assuming voltage is 60 hertz. So the current drawn by any load connected to 60 hertz is also 60 hertz. So in that case, why would the frequency be 120 hertz? Let's check it out. So most of the time, power engineers, we deal with RMS values, we deal with phasor diagrams. In real life, those don't really exist, right? In real life, we've got AC signals, but they move so fast. I always like to say during class, if I stick my meter in the wall, right? This socket, this receptacle my computer's plugged into, if that meter could display the exact voltage, not the RMS voltage, effective voltage, but the actual voltage, what would that meter read? If it's, say it's 120 RMS voltage standard outlet, and my meter could display the numerical value of the voltage at the exact moment, what would that meter read? What would it read? 169? That's the maximum voltage. Ahmed, is the maximum voltage what it always is? I'll tell you what, those numbers would flash so fast I wouldn't be able to read them, right? Here's what our voltage looks like in real life. If we've got 120 RMS, somewhere around here, right? We've got a peak value or maximum value Vm of square root of 2 times 120. And if I have a frequency of 60 hertz, then my period, when that voltage completes one full cycle, is what? 1 over 60 hertz. Meaning it goes through one whole cycle 60 times a second. There's no way I could read those numbers on my meter. That's why we use RMS. So in real life, they're alternating. Here's the formula for we can call it instantaneous or periodic. This is in the reference handbook in section 3141. But we've got let's look at just the voltage. The voltage with respect to time equals the maximum voltage Vm, which would be our square root of 2 times the RMS value, times, you can use cosine or sine, just depends on the reference. Reference handbook uses cosine, so we stick with cosine. But times the cosine of omega t plus any phase shifts. What's omega? What's the angular frequency? Typically, we're dealing with 60 hertz, right? In AC power. Omega is the angular frequency or angular velocity. It's converting frequency to radians per second. It's whatever that frequency is times 2 pi radians. Frequency is inverse seconds. Hertz is inverse seconds. Pi times inverse seconds is radians per seconds. So just like, let's see, who said it earlier? Let me dig through the chat. Who said earlier when I asked, why'd you pick B? You said S equals VI. Where'd that comment go? Austin. Austin said S equals VI. Here's the instantaneous or periodic version of that formula. Power is the product. What does product mean? Product in math just means multiplication times of voltage and current. Similar to when we're dealing with power in the RMS world, apparent power equals magnitude V times, that splinter is getting me today, times magnitude I, where these are the RMS values, right? If we're looking at the time domain or in radians per second, we got to use the instantaneous functions. Voltage with respect to time times current with respect to time. Just means we take this function and we multiply it, take the product of with this function. So I included the math in the book so you can follow along. You're not going to be expected to do this. All this math does is show you why when we multiply these two together, the frequency doubles. Once you follow along with this math, you'll never have to do it again. You're always going to remember it. So don't let this intimidate you. Don't let this think that you're going to have to do this on the PE exam. So look, instantaneous power. By the way, what are my units for instantaneous power? Here's another good gotcha. Here's another good trick question. What are the units of instantaneous power? It's a P. Anytime I see P, it's watts. Is that the case? What do I get when I multiply just the voltage and current, whether I'm dealing in RMS or in the time domain? When I multiply the voltage and current together with no power factor, see the trick? We get voltamps. Careful, instantaneous power, they use lowercase p, still voltamps. No power factor there. We're multiplying voltage and current. All right, so instantaneous power. We take the product of voltage and current. Here's our periodic or instantaneous voltage function, maximum voltage times cosine omega t plus any phase shifts. Here's the periodic, or we can call it the instantaneous current function, maximum current times cosine wt plus or minus any phase shifts. When you multiply this through, you end up with this relationship. Instantaneous power equals 1/2 times the maximum voltage and the maximum current, which, by the way, this is what? This is apparent power. And look look, what's happening inside our cosine. Look at that. When we're looking at just the voltage and just the current, what's the frequency of the voltage and the frequency of the current in radians per second in the time domain? It's what? It's just our angular velocity or the angular frequency. It's just omega equals 2 pi times where the frequency is in radians per second. T is the variable, right? T is our horizontal axis variable. Then we just got any plus or minus phase shifts. Typically, our voltage phase shift is what? Typically, we stick the voltage sine wave right on the vertical axis and we use 0 degrees. And then we know our power angle when we compare the current angle to 0. So look, we can get rid of, they use theta in this formula. That's not the power angle. Theta, when they use it here, I know it's confusing, is the angle of the voltage. But again, we usually use what? We usually use 0 degrees. Anything plus 0 doesn't change it. So if that's 0, look at this. What's this? Here's our power factor. Cosine of the current angle when the voltage angle is 0, or just the cosine of the voltage angle minus the current angle, that's always power angle. And then what do you notice about the frequency of P of t? The frequency is what? It's 2 times omega. 2 times the frequency of the voltage signal. 2 times the frequency of the current signal. So it's twice. We could say, since omega is 2 pi f, that 2 omega is 4 pi f, right? 2 times 2. But really, the only thing that should be standing out is this 2 right here. This 2 is the whole answer to this problem. We're multiplying the angular, tongue twister. We're multiplying the angular velocity or the angular frequency by 2. We're doubling it because we're multiplying the periodic or instantaneous voltage with the periodic and instantaneous current. And when we do that using trigonomic identities, we end up doubling what we're multiplying the t variable by. Does that make sense? A couple of quick graphs before we go. Look, here's a periodic voltage and current signal. We're using cosine instead of sine because that's what the reference handbook uses. Really, either is okay as long as you're consistent. But imagine this is our 0 degree reference angle of our voltage. Or we can say when we're dealing with cosine, the peak of our voltage occurs exactly at 0. This is the peak. If I were to draw the rest of the voltage signal behind this axis, let me see if I can get a nice curve. It would be descending. Does that look pretty good? In other words, this is Vm occurring at 0. Here's our current signal. I'm lagging the current signal a little bit just to show it. But we got 1 period of each. I took these signals in Desmos when I graphed them, and then on the same image, I multiplied them together, and I graphed that on the same image. So in black is our instantaneous power, which equals V of t in red times I of t in blue. What do you notice about the period of our black instantaneous power signal compared to our red voltage signal and our blue voltage signal? Yeah, Lewis, in the book, it's everywhere any of this pops up, we got it labeled where it is in the reference handbook. But you're right, that's a good idea. Yeah, what do you notice about this black signal compared to the red and blue signal? The period is shortened by half, said Rana. A good way to say it would be the period has been reduced by 2, right? Or not reduced by 2, it's been halved. In other words, look, here's my period of my black instantaneous power function. I'm going to just match it in black. I go through tracing the black period. Here's 1 full period, and then look, it starts over. In the same time it takes the voltage and current signal to complete one period, the black instantaneous power signal completes two periods. The only way that's possible is if what? If the frequency has doubled, right? T, the period, equals 1 over frequency. If I double the frequency, we've now halved the period. All right, any questions? And we'll pick up on number 5 on next week's webinar. Good, it's been just about an hour. Any last minute questions before we go? Yep, why these are the same as the qualitative practice problems from the last semester. So that was the individual chapters of the book during the early release version. So I think about 60 to 75% of it's already published in the previous semester live class recordings. If you're on the unlimited package, yeah, same problems. And then we finished them, combined them, and that's the new book, 100 qualitative practice problems for the P exam. Yes, this is the latest reference handbook 1.3. If you're looking for those formulas, they are right here in the NCEES reference handbook under phasor transform of sinusoids, section 3141 AC circuits. Whole book references where you can find everything in the reference handbook. All right, I'm going to stop sharing here. So you guys can see me nice and big. Yeah, any last questions? Did you guys like this? Remember, every Thursday, I'm going to try to keep it up for all 4 weeks. So Tuesday, Wednesday is our live class. Thursday, we'll be doing these webinars at noon. And then Friday, I'm going to open up some private sessions for some of our enrolled students that I'm also going to make available as in a webinar format so that anyone can attend if they'd like to as well. So a lot of good opportunities for live learning. All right, everyone, thank you so much for joining. I'm going to go ahead and cap it now so we can stick to the hour format. If you have any additional questions, you know where to find me, right? Zach@electricalpereview.com. You can send me an email. You can say hello on our free online community for the PE exam at www.powerpehelp.com. That's also where I have the list of these upcoming webinars. All right, everybody. Hey, we'll see you next Thursday for the second book launch webinar. See ya.